by doing some here are experimental visualizations of pipe flow, and here are some unstable traveling waves that had been found numerically, and they said, oh look, the experiment actually does go through these unstable, these saddles here. Look, doesn't this look like this? Doesn't this look like this? Well, I may not have picked the right ones, but I may not have picked the right one. This one looks a little more like this. But I think, though, I didn't do this on purpose, but a lot of people find this to be quite controversial, too. I mean, I think this fashion, too, may fade. And I've heard some people say, you know how hard they had to look through the experiment to find anything that looked vaguely like those unstable? You know, you'll always find, if you look at a cloud, you'll always find it looks like something, right? It'll look like an elephant, it'll look like a flower or something. And so they claim, some people, that this work, which claim to show that during real pipe flow turbulence, you were visiting this state and visiting this state and visiting this state, which had been well computed, that was kind of, I mean, we know there's extreme dishonesty in science. That's when you fake your data. But we know there's many gradations where you say, oh, well, that's an outlier. You know, everything else fits the theory, right? And you don't report your outlier, right? And you know, there's many gradations, and so some people claim that this is kind of like that. You look at all of your pipe flow, and the parts that don't look like the unstable, you say, well, they don't count. I'm going to take those. But I say that this question will be answered when these articles are no longer cited, or when they are cited, when just one group of them is cited. Right now, there are so many competing theories and so many theories that have gone out of fashion that you know it's an unanswered problem. Yes?
In the numerical figures, just curious to notice that it has quite well-defined patterns.
Yes, yes, I'm glad you say that. This is someone who has been attending my class. Right, indeed, if you have, this, you can see this has O2 symmetry, right? You now know O2 symmetry. Indeed, steady states are most likely going to retain some part of O2 symmetry. They will do something like, let's see, where's the class? Now this, what I'm about to say, applies to bifurcations, which is not what's happening here. These are just created. But you remember we made, I didn't talk about it very much because it was towards the end of the class. You start off with a big symmetry, and generally you break them little by little. You don't just go from something that is totally symmetric to something which is chaotic. Which I don't mean chaotic, which has no order at all. Here was another example of one of these things. Here's something with O2 symmetry, and this is bifurcations that lead to DM and DN. DM and DN are what you're seeing here. That is to say, you are seeing something with, has fourfold symmetry, but not quite. It's got a direction, so it's not D4, it's Z4. No, I think it's even, no, it's not, it's Z2, actually. It's Z2. This, and then you turn, because of these things are spiralish, the only symmetry operation that leaves it invariant is a rotation by pi. So this is Z2. This thing here is Z3. You can rotate it by 3. And this thing here, I guess it's also not symmetric probably. And it's 1, 2, 3, 4, 5, 6. It's a Z6. It's a subgroup of O2, and that is normal. It is normal to find that unstable steady states, or that steady states in a system are more symmetric than having no symmetry. Okay, we come then to a little bit more. I promised you a little bit more explanation of the what was called by Walef the self-sustaining process, and what was called by Phil Hall, your very own Phil Hall, who's here, the vortex wave interaction. And I believe this work started in 1991, but you mentioned a different author. You think 1991 is the right history, approximately?
I think it probably is Hall and Horseman, Hall and Smith. I think we're the same.
The same, okay. And here you see your very own Professor Hall and your very own Professor Blackburn right here in front of you. So here's what the idea is. This is plane Couette flow. So view this as plates. I'm moving here. A roll is a solution that does this. Okay, and it's not too, I should say, all this is kind of presaged by working convection. Think how many times we looked now in these last days in class, we looked at something not where there were walls that were moving, but just a hot wall and a cold wall. And we said that what happens is convection, and we drew the simplest kind of convection, which was rolls like this. How many times did I make this gesture of these rolls? Now this is not convection, that's not what's happening, but this is the same solution. And again, among the first people to look at it, this Nagata, who I mentioned, he did his PhD thesis with Busa, the Busa that I've mentioned, and the Busa balloon, the one who did so much to study rolls in convection. So it's not surprising that this was what was found and what actually exists. So these are the kind of rolls that you find in convection. Not to say that this is a solution, unlike in convection where they are a solution. But let's just imagine that we have rolls for the moment, even though they're not a solution. And perhaps you can tell us more about this how this works. And I will again have a part after the class that talks more about this. These rolls, what do? Well, we saw this, or maybe I didn't emphasize it sufficiently. We saw it in the context of convection. If you have no convection, then you have hot, less hot, less hot, less hot up to cold. That's what your isotherms look like. And once you have the convection, the isotherms bend. You're bringing hot fluid up, and you're bringing cold fluid down. So your isotherms do not look like this, they look like this. The hot has been brought up, and the cold has been brought down. Here, there's no temperature, but there is, the equivalent here is the flow in the streamwise direction. So you could look at the plane Couette flow in the same way, where you have these two plates, and this is your streamwise direction, and you say, this is moving this way, this is moving this way, at this speed, at this zero speed, a little negative, more negative, until I get to the top plate. You could say that, and if you looked at contours of streamwise velocity, you would see straight lines. Similarly, if you had rolls, that's going to bring the fluid that's moving this way up, and the fluid that's near the top, that's moving this way, down. So your contours of the amplitude of the velocity that's heading towards you in what I'm showing you here are now bent in the same way as temperature contours. And that's what you see here by these pictures. You see the bending of these streamwise velocity contours. And you see, you can follow the arrows. The top part is, let's say it's red. It's moving at a red speed. And the bottom part is moving at a blue speed. And you see that red is being moved down. So that's the fact that this red is no longer straight, but has a little bit of stuff here. And the blue in the center is being moved up. And you see that here, you see a little blue hill. Okay? And this thing here, if I'm not mistaken, is the former mid-plane, where the velocity was 0. It's now oscillating here, oscillating in space, not in time. Okay, so this is an effect. There's nothing. This is mere advection. Right? If you put some hot stuff here and you have some current going by, the hot stuff's going to be there, not here. This is no more mysterious than that. Right? Everybody agree with that? That's what that term U dot grad T does, and in this case U dot grad U. It takes whatever's here and it moves it there because the fluid is moving. It's like wind, right? Okay, if you have some cloud here of smoke and you go, it's going to be over there, not here. It's as simple as that. So that's what this is. And this thing is called a streak. What streak is, is you take the dependence on the span-wise direction. There didn't used to be any dependence on the span-wise direction before you made this whole system with the rolls and the streak. You see that now there is. The dependence in the span-wise direction of the contour, of these contours has now appeared. And that's what a streak is called. What a streak is called. That's what's called a streak. Okay, is now that these red, and blue contours have structure in the span-wise direction. Okay. And now comes another part, which is that this span-wise dependence of U is unstable, or not quite, you'll say, but
Equilibrium is.
equilibrium is
neutrally
neutrally stable, neutrally for very high Reynolds number, right? Below that is probably not neutral,
stable.
No?
It just
Always
depends
neutral?
Because they have to have an amplitude of the wave.
amplitude.
So it's the amplitude of the wave that drives the roll that produces the streak, all ties together.
Okay, so it's not that this is unstable, but it certainly doesn't mind becoming wavy. And that's what's drawn here. You can see that there's a structure now. We recall our symmetry. We've started off with something which was featureless in the streamwise direction and featureless in the z direction. Featureless in the streamwise and spanwise. There was flow in the streamwise direction. That's why it's called the streamwise direction. But if you looked here, and you looked here, and you looked here in streamwise direction, it would all look the same. And same with spanwise. You moved here, moved here. It was not featureless in the cross-channel direction. Here, remember, I say this to emphasize the concept. So here you're near the wall, here you're further from the wall, nearer and nearer. So the points in y are different from one another. But the points in x and z were not for plane quick flow. Now they are. You can see they are. Here you're going up, here you're going down. This is the spanwise direction in which before there was no structure. But there's still no structure in the streamwise direction. Right? You can see here, every point here looks the same. At this point, you break that symmetry, and you can see that you have this little thing here, and then another thing here, and another thing here. So this is meant to show that this is that this varies in the streamwise direction, and you see that. So you see, you are using x for the streamwise direction.
No, that's right.
Okay,
They do.
they do. Oh, that's not from this paper.
Yeah, but
Oh, but you just
I had
did.
to change
Okay,
notations.
all right, okay. I believe this is from this paper.
Yeah, yeah, it
Yes,
is,
okay,
yeah.
right. So, so now, not only are there these rolls that do this, and that bring up the the positive velocity and bring down the negative streamwise velocity, there's also, these rolls are undulating a little bit, and as are the streams. The whole structure is doing a little bit like this. And now, by a mechanism that I'll talk about much more later, this, so this, we can say e to the I alpha x, and nonlinear interaction is going to put together e to the I alpha x with e to the minus I alpha x, leading to something which is streamwise invariant. And that thing happens to reinforce this. Had that part right? More or less?
Well, if you, no, there are Reynolds stresses. If you take the stream.
Well, that's why I said e
if
to
you
the I
take
alpha x
stream-
times e to the
yeah,
I alpha x.
They do vary in x.
But that's why I said e to the
Yeah,
I alpha
they
x times e to
vary.
the...
They're not constant in x. They vary in x. You have to take the streamwise average of them.
But I thought that's exactly what I'm doing. When I say e to the I alpha
Okay.
x, that's variation. And when I say times e to the minus I alpha x, that's Reynolds
Oh,
stress,
okay,
because I have
yeah, sorry.
multiplication.
And then there'll be another.
And then
thing for
there's, that makes e to the 2 I alpha x
Okay.
and e to the minus 2 I alpha x, yes, all that stuff.
Fine.
But it also makes a zero component.
Correct.
So something wavy interacting, interacting nonlinear with something that is wavy, creates, among other things, e to the I alpha x times e to the minus I alpha x, creates a constant in x component, which, if you look at it, contains stuff that looks like this. And that is the cycle. And there were predictions that they made long ago, before there was computations, that this, they did it with asymptotics, about the strength of these rolls, that this would go like 1 over the Reynolds number, and that this would be much stronger, because Reynolds number is supposed to be big, so 1 over Reynolds number is small, and then this is much bigger. And then they had a prediction of this, that this was the dependence of the amplitude of the mode that looked like e to the I alpha x. And all that was borne out by later, okay, you can imagine in 1991 they were, especially with the people involved, they were not doing numerical computations, but later, in these times here, in 2010, 2013, they verified that this was the case. Again, the original authors will not say it needed no verification, no more than you need to verify that the derivative of sine is cosine, you know that, but for some of us, it was reassuring. Would you say that?
Yeah.
Yeah. Okay. Right, so that's this, what was called the self-sustaining process by Walef and discovered around the same time by Hall and his collaborators in the early 1990s. And notice then, this illustrates some of what I said. Remember Square's theorem. Square's theorem said, let's look in the XY plane, the Z plane, the spanwise plane. You know, there's no linear instability there because the instabilities are in the streamwise cross-channel plane. That is to say, the structure is in the streamwise cross-channel plane. And that's not true. Notice, everything we're seeing has either no streamwise dependence here or very weak streamwise dependence. These waves, yeah, they're doing this, but they don't just stop, you know, plus, minus. It's either not or weakly dependent in the streamwise direction. So that's a complete shift of geometric paradigm. Before the 1990s, people were looking for structures, 2D structures in the streamwise cross-channel direction, and now they're looking much more in the cross-channel spanwise direction. This variation in the spanwise direction is viewed as what's important. So a complete, you know, sometimes you say, oh, his idea is shifted by 180 degrees. Well, these ideas shifted by 90 degrees, literally. People started looking for things that were independent of X, and dependent on Z. Okay, so now I talk about, okay, I shift from this to, well, let's see, maybe I can take a little break here and I can go to some papers I was just looking at now that go with some of these ideas. No, yeah, he hasn't made any of these things. No. Well, I'll have to do it later. I'll do it later. Let's see. Well, okay, I can show you some of these books. Okay, these are papers by Gibson et al., and Svetanovich and Halcrow, who were indeed computing all of these unstable steady states. And so you see, here's a long list of them. They all have different, they have different appearances. This is some of them. They look like, I mean, they all look kind of the same, but it's the way, you know, if you take a parent to school of little children, the parent will be able to pick out their child's picture, even though the pictures all look alike to everybody else's parents. So if you're in this field, you would say, oh, that's TW2, of course. How could you mistake it for TW1? TW1 looks completely different. Anyway, there's a whole catalog of these, EQ 0 to 11, and that's just the beginning. There's many more. And again, here I was drawing this picture, and here's this picture drawn for real. This is dissipation as a function of Reynolds number for some of these different branches. Right? And again, this is just a very, very small sampling of what necessarily exists. There are probably hundreds of them. And that is not because plane Couette flow is special, or is turbulent, or this or that. I found the same thing in convection, which was not special, which was not turbulent. It's just that Navier-Stokes and Boussinesq equations, all these nonlinear equations, they do that. They form many unstable solutions. So again, this is just the beginning, so this is true for sure. The question is, does turbulence consist of traveling between these different? Does this have anything to do with turbulence? Does this have anything? And that is an unanswered question. As I said, I have a similar picture for convection in which some of them are stable, some are unstable. And what the system does is it just goes to a state and just sits there. There's no turbulence there. Or with a different initial condition, it goes to a different one and it just sits there. So having many unstable steady states does not imply turbulence, not at all. In fact, hold on, I think I have a picture of also someplace here. Well, okay, I don't have quite a picture of my bifurcation diagram, but here, these are many different, this is the same Hoffes did that work in plane Couette flow. This is convection in a cylindrical domain, you saw the kind that I work on. And all of these states exist at the same Rayleigh number. It just depends on the initial conditions, on the history. You could heat it up high and then bring it down, and then bring it down more, and then bring it back. So there's tremendous multiplicity of steady states. Many more than this if you count the unstable ones, but this does not lead to turbulence. Okay, so I think I'm finished with that part. Let me now talk about a particular aspect, say, of what happens in plain couette flow. And this was discovered in the early 2000s by Prigent and Dauchot at Saclay in France. This is a plain couette flow apparatus. Of course, I've been making motions as though you can move plates like this. You can imagine it's difficult to take very big plates, keep them exactly parallel, and move them and make it big. What they do is something simpler, which is they have plates that don't move, and what they have is a film, that a very thin film that an infinite belt, you see, that's moving. So although the plates aren't moving, you can say that the surface of the plate is moving, since that film, imagine saran wrap or something, or something a little more rigid, well, maybe, I don't know what they use, is being made to move. So this is how they make their plain couette flow. So they don't move the plates, they move the film. And this is an experimental picture. And what you see here is a surprising thing. You don't see just turbulence. You clearly see, even though it's a very fuzzy experimental picture, you clearly see these stripes. And this is the streamwise direction, the spanwise direction. You see that these stripes are not in the streamwise direction nor the spanwise direction. They're at an angle of 24 degrees, more or less. And they have a quite well-defined spacing of 40 half gaps. As I told you, the convention in plain couette flow is that this distance is 2. So a half gap is 1. So there are 40 half gaps. So it's not like convection rolls. You recall how many times we said that the rolls were approximately round. That is to say, the roll was about as wide as it was high, and since this distance says 1, then this distance 1, and so the wavelength was 2. And in terms of half gaps, I guess it would be 4. This is much, much bigger. So these are not those rolls that we were just talking about. The rolls that we were talking about just now when we looked at the work of Hall and Sherwin and Blackburn were rolls that are approximately round. But this is not. You could say that each of these little white things, I don't think the picture's good enough for that, but imagine that each of these little white things is a roll. So this organization is really remarkable. This stripe consists of a whole bunch of little rolls that just sort of kind of stop here and make laminar flow and then start again, and they know about each other such that they can form these stripes. So this, I'd like to say that I could give you the explanation of this, but I do not have I have a lot of facts, but not the explanation of this. This is a remarkable result. And it turns out that this is a generalization of something that had already been seen in Taylor couette flow. This is a picture from Taylor couette flow from later, 1986, the group of Swinney et al. It's a group where I was a postdoc, and hence you can know why I'm mentioning it so much. So this is from an article by Andrek et al., but it's the same phenomenon that was described in 65 and 66 by Coles and Van Atta, who were giants in fluid dynamics at Caltech. And you see here, although not that clearly, you see this spiral turbulence here, and here laminar. That's what you're supposed to see anyway. That's what they saw. And this is in a cylinder, an apparatus that has aspect ratio 0.88, meaning that the ratio of the inner to the outer is 0.88. This is approximately to scale. So what did Prigent and Dauchot do? They did Taylor couette. This is the whole circumference. There are mirrors here that permit you to see the back. Not here. Here you're just seeing the front, but here you're seeing all three of them. And this is actually realistic. They did a much higher aspect ratio, 0.983. That means that the ratio between the circumference and the distance between the inner and outer radii is much, much bigger. So this is a much bigger experiment, if you like, by making this gap thinner, by making the inner cylinder almost as the same size as the outer one. You get much more room in the circumference there. And so the mapping, quantitative, is like this. That is to say, this Taylor couette apparatus fits about like here. So here you see that you would just see kind of one of them. And not really, because there'd be edge effects that would keep it from being very... Here, here they noted, oh, look, we have a piece of turbulence and a piece of laminar, and it persists, it just stays. That's strange. But here they could say not just that, but because it was so big, it has a regular structure. These people they knew there was laminar and turbulent, but they did not know that it had a regular structure, a regular wavelength, and a regular angle, because they just saw one of them. Okay, so this is remarkable. Again, this is not. I'll be doing a little bit more about telequark flow. This is not a remarkable picture at all for someone who studies telequark flow. This is one of the normal things that you see in telequark flow. But what you see normally is this thing here should be about the size, or the same size as the gap in the inner and outer. This is like a convection. I mean, the picture that you usually see in telequark flow, there are things that are like convection rolls, except that they're not convection. They're transporting angular momentum in the same way that you transport heat. And they're rolls that are approximately round. They're the same size as the gap. And if you counter-rotate, those things become tilted and you get spirals. But it has nowhere near this size. Again, this is not the size of the gap. This is 20 times the size of the gap. And this is not flow that goes up and flow that goes down, flow that goes up like a regular roll like that. This is laminar turbulent, laminar turbulent, laminar turbulent. So again, these are the same kind of things that you see in pattern forming systems. But you don't see hot, cold, hot, cold. You see laminar turbulent, and that is it's not understood. What does that mean? That you have a patch of laminar and a patch of turbulent, and that it wants to make this angle, and that it wants to make this spacing? Why does it do that? And this we still don't know. We know many things about it, but we still don't really know the answer to that.